if you take any point on the boundary, then its modulus is going to be 1 because J is defined as A plus iota b, and then modulus of J will be under root of A square plus B square, and since A and B are coming on the boundary, so and it is a ball of a center 0, so A minus 0 square plus B minus 0 square is going to give you 1. So because of that it comes 1. So let f is a function, a continuous function on this surface S1, and define for z belongs to b of 0, 1 such that u of z is equals to 1 over 2 pi integration 0 to 2 pi function of z plus e to the power iota t over 1 plus z r e to the power iota t dt. Then u is harmonic in this ball B. We are not taking the closure, we are not taking the boundary. We are saying that U is harmonic because when we talk about the harmonic function, then we say that its second order derivative exists. And when we say that its second order derivative exists, so what will be the condition for the existence of the second order derivative? The first order derivative should be continuous, isn't it? But on the boundary, we cannot say that its a first order derivative is going to be continuous or not. So because of that, every time when we talk about the harmonicity of a function, we define it in the inside of the domain, and on the boundary we give some boundary condition that on the boundary the function is going to give you this value and this value and this value, whatever kind of boundary you have given. If you are provided with a rectangle boundary, then we put the condition on the sides of those rectangles. If you have a circular boundary, then as soon as you say that the boundary is a circular, that the domain is a ball or a sphere, in that case after every 2 pi it is going to give you the same value. After every 2 pi it is going to, so that is the periodicity condition. And the second condition you put, that is provided like when r is fixed. R is fixed, so at r equals to a, the second condition is given, and at that moment we use the Fourier series value, Fourier transform series to calculate the value of those coefficients. So you are very much aware of all this property because in the last classes we have studied a lot of problem like the Laplace problem on a circle, Laplace problem on a sphere, in a cylindrical coordinates, in a rectangular coordinates. So you have idea how to calculate those things. Then U is harmonic in B01 and a continuous extension of F into the open unit disk. So we can see that the solution U of a Laplacian equation in its closed form is the real part of the function g of z is equals to 1 over 2 pi integration 0 to 2 pi. We have already approved, like in the last classes, we write the solution of Laplacian equation in the term of the Fourier series, and then we calculated the coefficients, and then to make it a closed form solution, we did some kind of simplification, or you can say that we did some kind of arrangement to write it in the form of a complex function, and that complex function was coming like this. Now f of e to the power iota t is coming, so basically it will be f of cos theta plus iota sin theta, and when we are taking only real part of this function, so that was the boundary condition that was defined on the boundary of that uh, circular region. So this boundary was supported by the function, this that function in the real part of this function was known as, what was the real part of this function? The boundary was supported by in the Laplace problem when we were talking about the closed form solution. So we write its real part, and then we say that this boundary f of theta is supported by a function p of r comma theta, and this p r comma theta is known as Poisson kernel. Have you guys forgotten about that? So this supported function, basically this is supporting the velocity potential, so it was known as the Poisson kernel, and the whole integral was known as the Poisson integral formula. Please do revise the previous thing because
Oh yes, 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 yes. Yeah, you have the Poisson integral, and then you use the Poisson kernel to integrate the function that you want to obtain, right? The like you have the Poisson kernel multiplied by another function.
yeah, that is the
F
function, that is the value of the function at the boundary of the circular
at the
region.
boundary. Yeah.
So this was the, like, this is the thing which we are following. Now we are going to say that what we did, just try to understand. Just I'm writing in three dimensional. It's a sketch. So I said that this was your sphere, and this was the domain omega. Say this is the radius of the sphere, and then this function f was defined on the boundary, and that boundary function was supported by this Poisson kernel. Now what this theorem is saying, this theorem is saying that the solution of this Laplacian equation, whose value at the boundary, like at a comma theta was f of theta, is nothing, the general solution u of r comma theta is nothing but the continuous of this boundary. So this theorem is trying to say the same thing, that the general solution of this Laplacian in this unit disk is nothing but the continuous extension of the function defined on the boundary of the unit disk. Is it clear? What is the statement of the theorem is clear?
Yes.
But since here we are not talking the things in the real space only, rather than we are taking the complex space. So it is generalizing it. Like the complex space is a bigger space than the real one, because the complex is basically r cross iota of r. So it is a bigger space where we are talking about this thing. Now, according to our previous discussion, which we discussed in the last classes, the solution of the Laplacian equation, the real part of this function was going to be the solution of the Laplacian equation. This was the solution of the Laplacian equation, and the imaginary part is going to be iota of v. Even when you will check that v separately free from iota, in that case v is also going to satisfy the Laplace equation. V is also going to satisfy the Laplace equation. So u is harmonic function, and even when you will check, then you will find that v is also going to be the harmonic function. So the summation of harmonic function with the conjugate with the iota of another harmonic function like u plus iota b is going to be a holomorphic function in the complex space. Now z is
I wanted to ask if harmonic function it's a holomorphic function or it's the converse that is true.
mm, so basically
Or
what is the
yeah,
harmonic function? Harmonic function is defined in the real space, isn't it?
yeah,
And holomorphic function is defined in the complex space.
yeah. If a function is holomorphic, then it's analytic, right?
Yeah, it is analytic. So analyticity is different thing, but if you will try to connect the harmonic function to the holomorphic function, so the only difference is that the holomorphic function is the summation of two harmonic function with linear combination of two harmonic function a u plus v where v is nothing but iota. Like one constant it is speaking from the real space and one constant it is speaking from the imaginary space. So this is basically what you are you can say that it is the not linear combination. I would say that it is the combination of two harmonic function, one in real space and one with the iota multiple of the harmonic function.
Okay,
Both are harmonic, u and b both are harmonic, and the holomorphic function is going to defining the complex space, so it will be coming like u plus iota v. Now this is holomorphic because u and v separately in real space are harmonic function. So u is harmonic, it means Laplacian of u is 0. V is harmonic, it means Laplacian of v equals to 0. So when you are going to calculate the Laplacian of z, then still it is going to be 0. So in the complex analysis, we use Morera's theorem to prove the holomorphicity of this function z. But since we already have computed the solution of the Laplace equation and the real part of this solution is going to be the solution of the Laplace equation, so u was harmonic, and if you check then v was also harmonic. So because of that, like by differentiating under the integral sign, you can directly say that z is going to be the holomorphic function because we have already done those calculations in the past classes. Hence, u being the real part of z is harmonic in the unit disk to see that u is a continuous extension of f inside the unit disk, we note that limit of z tending to e to the power iota theta j plus e to the power iota t and 1 plus j bar e to the power iota t. So when you will take the limit, simply j is not e to the power iota theta is not equals to minus e to the power iota t. This is the case. Take this e to the power minus iota theta outside. So this limit is going to be the e to the power iota theta except the case when this, since f is continuous on the compact set S1, it is bounded on it because S1 was the closure of this boundary. So S1 is going to be a compact S1 is going to be a compact set, and also F is continuous, which is defined on S1, that is a compact set. So by the theorem, what is the name of the theorem? I don't know, but by the theorem of the topology, it is
Heine-Borel.
Hein-Borel theorem. So it is. I think it is the lemma based on the Hein-Borel theorem, not exactly the Hein-Borel theorem. So it is bounded on it, and by bounded. Actually, I wanted to avoid some proofs of the theorem, but I could not avoid the theorems because that is some necessary, like some important part of your syllabus to proceed to the Perron's method. So sorry for that. So by the bounded convergence theorem, because here are some students who haven't studied the mm, functional analysis and measure theory, so it might be little bit difficult for them because somehow partial differential equation is combination of geometry, fluid, functional analysis, and at some places you can say the topology. Just pass this limit inside of this function f, that is a continuous function. So this limit is coming to d to the power iota theta dt, and this is independent of t, so it will come outside, and the integration 0 to 2 pi dt is nothing but 2 pi, so 2 pi and 2 pi will be cancelled out, and here we can say that hence now let's write the various form of the Poisson kernel. the function k omega z for omega not equals to z is also called Poisson kernel. For let's take a very simple case for modulus of omega equals to 1. This will be nothing but this kernel defined in this form. So for omega equals to 1, modulus of omega equals to 1, it takes the form k of e to the power iota theta comma z 1 minus modulus of z square over modulus of e to the power iota theta minus z square. Here, since modulus of w is 1, so if we say w equals to e to the power iota theta, then automatically, using the property of the complex analysis, modulus of w is going to be 1 because cos square theta plus sin square theta is going to be 1. So, if we set w is equals to e to the power iota theta and z is equals to r e to the power it, and then Poisson kernel takes the form I am not doing anything new, I am just making the arrangement to write the different form of the Poisson kernel in the complex plane, not in the real plane. So, k 1 minus r square and modulus of e to the power theta minus r e to the power iota t square. So cos theta plus iota sin theta minus r cos theta minus iota r sin theta. The modulus of this is going to be cos theta minus 1 minus r whole square plus sin theta 1 minus r whole square, and when you will have to take the square root of, and when you will make the proper arrangement it will be coming like 1 minus 2r cos theta minus t plus r square. So this can be written as 1 minus r square over another way is to write just take e to the power iota theta common, so it will be 1 minus r e to the power iota t e to the power minus iota theta, and if we apply this modulus, so value of the e to the power iota theta is 1, so it will be that can be written as a function of 1 plus r e to the power iota t over 1 minus r e to the power iota t. And if we take the expansion of this series, then it is basically the sum of the series 1 plus 2 summation and varying from 1 to infinity r to the power n e to the power I n t r. You can write summation n varying from minus infinity to infinity r modulus of n e to the power I n t. It is more complex thing, you can just ignore this thing. Don't focus on this part. Subharmonic functions. And their properties. So subharmonic function is a special kind of function. Basically, it is harmonic, but it satisfies some more property, like how we define the subset of a set. So subset of a set does not contain all the numbers, but it satisfies all the property. Like if you define the subgroup of a group, so it satisfies all the property of a group, but it does not contains all the elements. But to define the subharmonic function, I'm going to write a theorem, and if it satisfies any point of that theorem statement, then it is going to be a subharmonic function. So let omega be a connected open set and V from omega to R be continuous. Then the following are equivalent. First, for every region D which is contained in this omega whose closure is compact and the closure is also contained in omega, and for every function u continuous on this closure and harmonic within the domain D, harmonic in domain D if V is less than or equals to U. On the boundary of D, then V is going to be less than or equals to U on D, and hence also on the union of this thing. So basically, this function V that is defined from omega to R, sorry, omega to R, then this function V will be called as a subharmonic function if you are able to find a region D that is contained in omega and U is a function, U is a harmonic function in this subregion omega in such a way that U is continuous on D bar, then V is going to be less than or equals to U in the D closure. So this is the subharmonic function. A subharmonic function V is defined from a region omega to R if there exists a harmonic function u which is defined in the subdomain of omega, in the subdomain of omega, such that u is harmonic within D and it is continuous on the boundary of the D, and it also satisfies the property V is less than or equals to U, or you can say that this harmonic function which is defined on D is always going to be greater than or equals to this function V. In that case we call the function V as a subharmonic function. So this is the property, but it satisfies the fourth property. If it satisfies this property, then it is going to imply the another one, then that is going to imply the another one. So let me write all the property. So for every point P belongs to the omega, and for every disk with the center P and the radius R whose closure is contained in omega, we have V of P is equals to 1 over 2 pi integration from 0 to 2 pi V of P plus R e to the power iota theta d theta. Third, for every point P belongs to omega, and for some disk B P comma epsilon which lies in omega, for ADR V of P is less than or equals to 1 over 2 pi integration 0 to 2 pi V P plus R e to the power iota theta d theta. And the fourth point is that for every region D contained in omega, and for every U harmonic in D satisfying V is less than or equals to U, either V will be strictly less than U in D or V is equals to U in D. So when we have some theorem in which we have to prove that all the points are equivalent, so what is the starting point? If there are 4 points and we have to prove that these 4 points are equivalent, so we have to prove in this way that first point implies the second one implies the third one implies the fourth one, and again in the round circle fourth one is implying the first one. So this is the definition of the harmonic function. This is the definition of the subharmonic function. Basically what it is saying, it is saying that if V is any function from omega to R, only property we have given that it is a continuous function. Then if we are able to find another function u which is defined from D, that is a subregion of omega to R, in such a way that u is harmonic inside D and u is continuous on the boundary of D, and also it satisfies the property that u is always greater than or equals to V. In that case V will be harmonic function, And rather than saying it a harmonic function, we will call it a subharmonic function because it is less than or equals to u throughout the domain D. So this is the property of a subharmonic function. Now we have to prove that these four statements are equivalent. So proceed in a systematic way. We will proceed from 1 to 2 to, this is a very easy theorem. You have doubt in the statement, then you may ask to me. First to 2. For let B P comma R be a disk whose closure lies in omega, and let W be the harmonic function in B P comma R, which agrees with V on the boundary of, then V of P is less than or equals to W of P. And by the mean value theorem, the value of W of, since we are defining W in this disk, so value at the center is going to be the average value in this disk. So that is the mean value theorem. So by the mean value theorem, it can be written as 1 over 2 pi integration 0 to 2 pi V P plus R e to the power iota theta d theta. We are basically taking the extension because V that was defined from omega to R, and this B P comma R is a disk that is contained in omega. So the mean value at P can be written as, or you can also write it at the extension of this function on the whole domain. Where inequality on the left follows from equation number first, and the equality on the right hand side is due to the mean value property of the harmonic function W. So just notice this point, V is less than or equals to W of P. From where it is coming, we have given from the first point, that if D is any sub-region of region omega, if D is any subdomain of the domain omega, whose closure is compact and contained in this omega, then for every function, for every harmonic function you defined in D and whose, and this function U is continuous on the boundary. We are not talking about the harmonicity on the boundary because at the boundary it might be differentiable or not. So that's why we are talking that U is continuous on the boundary and U is harmonic inside the domain D, such that V is less than or equals to U on D. And then if this condition is given, that if V is less than or equals to U on del D, then it will implies automatically. And in that case it is satisfying on D and it is satisfying on del D, so it is satisfying going to satisfy on the D union boundary of D, that is, it is going to satisfy on D closure. So the same thing here we are saying. For the convenience, we are taking a disk whose closure is D. The closure of this disk is defined as SR, basically according to our definition. So let B, P, comma R be a disk whose closure lies in this domain omega, and let W be the harmonic function in this closed domain, in this closed disk, which agrees with V on the boundary of the B, P, comma R. So what it is saying, V P is less than or equals to W of P on the boundary of the domain B, P, comma R. Sorry. So for this, since we are defining it in a closed disk, so we can use the mean value theorem in the form of iota theta. So using the mean value theorem, we can write this, and then it will be simply the second point. Next, it is saying that for every point P belonging to omega and for some disk B, P, comma epsilon. So every time, suppose you are choosing this domain omega and you are choosing this point, say P1, you form a disk. You choose another point P2, you form a disk. If you are choosing a point P very near to the boundary, so the radius is going to decrease. If you are choosing here, then the radius will be more small. So any point P chosen inside the domain omega in such a way that for every point P you are able to find a small radius epsilon, so that you can form a disk B, P, comma epsilon, which lies in the omega and also its closure lies in the omega. Then for this reason it is going to satisfy. So the same thing, what you will do, you will choose the closest point nearby to its boundary and you will choose the smallest epsilon, and then this property will satisfy because of the mean value property and the property 1. And then you can vary epsilon from the closest point to the largest point, like you can define a big radius, and this will hold. So the second to third statement is trivial. I'm not going to prove that. From third to fourth we are going to see. Let U is harmonic in D, satisfying V is less than or equals to U, and assume W is equals to V minus U. Then W is less than or equals to 0 in omega. I am stopping this class here. Tomorrow I will continue, and most probably tomorrow I will finish the Perron's theorem. If you have any doubt, then you have 2 to 3 minutes, you can ask. Are you guys here in the class? Is everyone?
Yes, of course. Yes, 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 yes.
Okay, so
Yeah.
so if you have any doubt, then it is fine. I have to go, and we can extend the class tomorrow to finish this topic so that I can start heat equation this Wednesday, and I have prepared the lecture notes. I will upload shortly. So heat equation is going to be little bit easier because you know all the property, you know the Poisson kernel, you know the Poisson integral, you know the eigenvalue problem, you know the eigenfunction method. So all the things I am going to use in the heat equation. So basically, you can say that the heat equation is basically the not subset, I would say. I would say that all the theorem and all the method you are going to proceed in the heat equation. So you don't need to worry about the unit third. It is unit 4. It is really easier. It was unit 3, isn't it? The Laplace is unit 3. Yeah, so unit 4 is very easy as because you already know everything. So it is my request. Please read the eigenvalue, eigenfunction method, Bernoulli's Poisson kernel, Poisson integral, and the Heaviside function fundamental solution. Everything what you have gone through, so that if you have any doubt, then you can ask to me tomorrow, because the next week I'm going to take the exam. Okay. Okay. So see you tomorrow. Bye.
Yes.
Okay.
Bye.
Bye.